Hello, good evening friends. Today, this is a class for BSc third semester physics. I will continue the discussion which was left half in earlier class. I will continue the same on dielectric, theory of dielectric or electric polarization. Somewhere we have discussed this polarization density vector. Polarization density vector. We have written its expression. In other words, we define this electric polarization. This polarization density vector or polarization is given by this P is the polarization density vector, which is equal to, say, proportionality constant alpha into E, the applied electric field. We have written this. So this alpha is the atomic polarization. Alpha, the atomic polarization or polarizability. Well, we have written the expression for it, that is P is equal to P, the atomic polarizability, is given by 4 pi epsilon naught permittivity of free space R cube, the radius, into the field. We know that this vector is acting along the same direction as that of applied electric field, and this density vector we call it as polarization density vector. It is given by this expression. If there are n number of molecules per unit volume, even we can write this P, the electric polarization vector, n, the number of molecules per unit volume, into this, that is individual. Now this is a density vector. We can write this using this, that is n epsilon naught permittivity of free space 4 pi R cube into E, the electric field. Now, this we have discussed earlier. Now, this electric polarization vector or polarization density vector and charge density, there exists relation between them. So we'll try to obtain that relation today here. So the relation between polarization, electric polarization, and the surface charge density. Relation between surface charge density, and say polarization density. It's a very interesting article. In some book, somewhere in the literature, they have defined this polarization density, or we call it as electric polarization. In dielectrics, this electric polarization can be defined in terms of surface charge density. Surface charge density. We know that when a we place a dielectric slab, whether it is slab of polar molecules or a slab of non-polar substance. When we place that polar substance or non-polar substance in an electric field, so there is induced dipole or a permanent dipole, and this induced dipole or a permanent dipole, we write it as dipole moment. Say for example, this is a slab of a material, we call it as dielectric slab. Say this is Na and say Nb. We have seen when this dielectric material is placed in an electric field, what is the effect of the electric field on this material called as insulator? So polarization takes place. There will be induced dipole or a permanent dipole depending upon whether the slab is of a polar substance or a non-polar substance. Normally, when we place a dielectric slab in an electric field, these dipoles, they get oriented. We know this. Say these are the dipoles, say negative, positive. This is direction. I will draw them here. Okay. These are the dipoles. And they get oriented along the direction of electric field. Now here, this is negative, this is positive. We have seen this. This is negative, this is positive. Fine. This is negative, positive, and so on. Negative, positive, and so on. They get oriented themselves along the direction of electric field. So I have not shown here the direction of electric field. Fine. This is positive, negative, this is positive, negative, and this is positive, negative. They are the dipoles. Now, inside this slab, say here on the surface or on a molecular layer, there will be positive charges on Na as I shown here, and there will be negative charges. So what happens when we place this say dielectric substance, whether it is polar or non-polar, in an electric field? We know, we have seen, we have discussed that the dipoles, induced or permanent, they get aligned. That means the negative charge of one molecule and the positive charge of the next molecule, they becomes closer here, as we have seen. This is positive, this is negative, this is positive, this is negative, then come closer. So on one side, on an average, the negative charge is here, on the other side, positive charges. What happens inside? Inside the slab, since these charges are close to each other, the negative charge gets neutralized with the, say here, the positive charge of one dipole gets neutralized with the negative charge of the next molecule, and total net charges inside this becomes almost zero, except at the end. At the end of this slab, all the charges are positive, and on this end, all the charges are negative. These charges, they are not on the surface, they are within the molecular thickness of this slab. So this end becomes positively charged and this end becomes negatively charged. When this slab is inside or placed in an electric field, this picture appears to be here. So this molecule means this negative charges on an A or the positive charges, negative charges on an A or the positive charges on say B, you can say either A or B here, they will be within a molecular thickness of this slab. Right, they are inside and they are bound to be, right now they are the induced free charges. So here they are positive free charges, you can say. If you take a zoom picture of this for a single molecule, say this is a concept here. So this is say a dipole. This is positive charge, this is a negative charge, and say we draw this. Say this is negative charge and this is an angle made by this. This is a dipole moment here P. Dipole moment P of this. Now this is an A, this is positive and this is negative. And here we have this direction, that is unit vector. Suppose we know P is equal to the moment, dipole moment Q into dl. If this dl is this, if I write this as dl, distance between the center of positive charge and to that of center of negative charge. So that product Q into dl, either it is a negative charge or a positive charge, and the distance causes a dipole moment. We have seen this. Now this is, say this becomes dl cos theta. This is this when we magnify it, when we take individual molecule, say a dipole moment here constituting a negative charge with a positive charge and the distance between them. So dl cos theta is acting along this direction. One more component of this vector P will be along this direction. The point here is, if dl is the distance between a positive charge and the negative charge, or the center of positive charge and the center of negative charge. So this happens to be the diameter of a molecule. Almost approximately you can say it is a diameter of a molecule here inside the slab. And now if n are the number of molecules per unit volume, if I take small a is the surface area of this slab here, surface area of the slab. If A is the surface area, dl is the length, surface area, A is the surface area, we want to calculate the density here. And see, this theta is the angle between the density vector P and to that of a normal drawn to it, that is theta, the angle between the normal and the density vector, what is called as polarization density vector, theta, the angle between P, the dipole moment, and the normal or a unit vector here. So theta is the angle. Now we can write this as equal to, say, n are the number of molecules per unit volume. Number of molecules per unit volume. If these are the molecules per unit volume, say n, I want to write this as equal to. So the number of charges on this surface, that is A, or the number of molecules here on this side, that is number of charges on end A. At end A we have the number of charges. So let us calculate the number of charges on this side, that is N are the number of molecules per unit volume in a thickness called as molecular thickness layer. N, say A, the surface area, dl is the distance between the two charges, center of two charges, and this cos theta. So the number of positive charges induced at end A or the number of negative charges induced at end B. So we can, the induced surface charge density, let me write, induced surface charge density. And this induced surface charge density, we can write this equal to, say, N A dl cos theta into Q. Q is the charge either on end A of this slab or on end B. So this is, say, what is called as the induced surface charge density. We can write this as by symbol sigma p. Sigma p is equal to, say, charge density. We can write it as, say, charge density sigma p. We can write charges per unit volume, say number of charges here per unit area. We can write, because it is a surface charge density, N A dl cos theta Q by A. This is number of charges per unit area. So this gives the number of charges in surface area A. So this gets, so sigma p, charge density, what is called as surface charge density. So N dl cos theta Q. Q is the charge either on end A or on end B. Once we write this as a surface charge density, we can say about this surface charge density, it can be written as sigma p, or it can be written as sigma I. I stands for induced charge density, or we can write this as sigma bound. In the sense, charge density due to free charges, these are the free charges on the in a molecular thickness of the surface. They are not exact on the surface, in a molecular thickness here at the end A and B inside. So inside no charges here, they get neutralized. So this surface charge density can be indicated as sigma I. It is induced or due to bound charges. Here you must get clear yourself that there are two types of charges when we study this, what is called as dielectric in an electric field. There are free charges as well as some bound charges. Does this bound charges take part in a conduction? So this bound charges, they do not take part in a conduction, and therefore we say the dielectric is an insulator. It is different situation arises when we talk about what is called as a conductor. The different situation you will feel or you will see here. Here it is a different thing. We are using a dielectric material, maybe polar or non-polar, in an electric field, and we are calculating what is called as the relation between, or we are establishing relation between surface charge density. You can say it is denoted by sigma p, and the polarization density vector p. To write this, we know, see, P is equal to Q into dl, P the dipole moment, or say polarization density vector. It is given, it's a product of charge into distance between them. So I can write this as equal to only its magnitude, say P into Q dl, or you can write this as Q dl cos theta, dl cos theta, or else you can write this is equal to P cos theta. Only the magnitude we have taken, P cos theta. When we take its direction, that is a vector P and the unit vector which I have shown it here, a normal, its normal component. We take this as its normal component, dl cos theta or P cos theta here, that is its normal component P and a unit vector. So this gives the total polarization density vector, both in magnitude as well as in direction. So here induced charge density, I write induced charge density, that is given by this sigma p, and this sigma p we can write either in some books or in literature they indicate as sigma I or sigma bound, that is equal to n, the number of molecules per unit volume, P cos theta. This is its normal component. So this can be written as P cos theta. Now sigma P can be written as, say, n P and then unit vector. Look at this. This is a density vector, what is called as polarization in dielectric, which is equal to induced charge density. Induced charge density. Sometimes this polarization density vector P is expressed in terms of surface charge density or surface charge density. It can be defined as well. So polarization is nothing but the surface charge density, that is magnitude wise. In special cases, when this is a different situation which we have drawn, in special cases where applied electric field E, when it is acting in the direction of induced dipole moment, this, so theta becomes 0 and cos of 0 is equal to 1, therefore sigma P is equal to, say, simply P, the polarization vector, that is in special cases. So here what we conclude is the induced surface charge density is equal to polarization per unit volume or polarization density vector. Induced surface charge density is equal to polarization density vector. I'll write here polarization density vector. density vector P. So this is the relation you can say. In other words, you can say polarization, dielectric polarization or electric polarization can be expressed in terms of surface charge density. After this, what we have in this article is a Gauss law in dielectrics. Gauss law in dielectrics. We'll discuss the Gauss law in dielectrics. Already we know Gauss law in electrostatics. It's based on the same definition, same theorem, you can say, same statement. We can arrive how does the Gauss law is applied in case of a dielectric medium. Only difference is that, and the statement and its proof will do it in the next article or in the next class, you can say. I have a small article, what is called as electric displacement vector. Electric displacement vector. Say it is denoted by capital D. It has its physical importance and the relation. Relation, say D is equal to epsilon naught, say E electric field plus P the polarization. Relation between D, E and P. Relation between say D, E and P. This is article mentioned in our syllabus. Well, what happens inside the dielectric? How does the field varies? Inside the dielectric, when a dielectric sample, whether it is polar or non-polar molecule or substance, is placed in an electric field, what is happening inside the dielectric? That has to be understood, and it's a big article, and fortunately or unfortunately it has not mentioned in our syllabus. So inside the dielectric material or a slab, the electric field, when a slab is placed in an electric field, the electric field gets modified and the field inside the slab, called as, when a polarization takes place, we write this is equal to E naught, the applied electric field, divided by epsilon naught, or you can say instead of that you can write in terms of polarization density vector, that is a negative sign. It shows that it decreases with this permittivity of free space. So to find this relation, electric displacement vector will define it, will find its physical significance and the relation between D, E and P. Normally they ask the question on this. Normally they ask what is the dimension of this. We have seen the dimension and unit of polarization, P, density vector. So what must be the dimension and importance of a displacement vector? It is called as electric displacement vector. So to know the magnitude, direction of this electric displacement vector t, we must know what is happening inside the dielectric sample when it is placed in an electric field. So I am not going in detail how to calculate that, but at least we can say there is a modification inside the electric field. There is applied field, and due to the applied field, the induced dipole or permanent dipole gets aligned, and once the alignment takes place, there are charges called, as we have seen in earlier article, there are free charges, surface charges, where we have calculated surface charge density, positive charges and negative charges, and then we have defined what is called as electric polarization density vector or polarization density vector. Inside the dielectric sample, the electric field is given by this relation P divided by epsilon naught. Epsilon naught is a permittivity of free space. Negative sign indicates that this quantity decreases as we increase the external applied field. There is a net field also. So what is called as the electric displacement vector and its relation, it is given by this relation. The net electric field, I will write it here, net electric field inside the dielectric. Okay. To find this, let me keep this as it is. I need this. EP is equal to minus P, the electric polarization density vector, upon epsilon naught. Now the net electric field inside the dielectric. Imagine I have a parallel plate capacitor. These are the two plates of the parallel plate capacitor. One is positively charged, and say this is negatively charged. I will take this as a negatively charged plate. Either show it on the other side, or this is positively charged plate. So there is nothing inside these two plates. It's a vacuum or empty space. There exists electric field. Say this is electric field. Starts from positive charge, goes towards negative charge. I will call this as